performance under these different situations. And the final thing I want to show you, here's a picture of a fetal picture, right? A little baby down in here at 8 weeks. One of the things that ultrasound has done is back in 1976, they decided, I don't want to worry about bioeffects, so what I'm going to do is sort of cap the bioeffects at the current standard. And what that standard did, one way to measure that is a mechanical index, which is 1.91. It draws it right here. So that says right now, if you want to get FDA approval for any of your devices, you cannot go past a mechanical index of 1.91 without, a lot of explanation and basically go through a PMA process, which is very painful and expensive. So, I was talking to Bill O'Brien, who's spent his career looking at bioeffects, which is really important for things like babies, right? And so the question that we ask is, why did they pick 1.91? It seems kind of arbitrary. There's no real physiological reasons for picking that. So we said, now that we have something that we can compare, let me look at my 3 tasks for lesion detection and study how the efficiency increases with mechanical index. So if I go above 1.91, do I get any net benefit? And it turns out I do. In fact, I think it's not as much as maybe this change as I getting here. So now we're going to start to ask the question, because I can rate performance, maybe it's time to revisit sort of these artificial bounds on how ultrasound is being, what outputs you can put out there, how much power you can put into a patient. So we're thinking of working with Bill to try to look at the bioeffects and couple that with performance to perhaps give some new concepts and ideas of where the ending should be. So here's my summary. What I want to leave you with is this whole idea of image science is very cool stuff. And I went to the FDA because I had the sense that cool things were happening there in the development of image science at the time. And I wasn't disappointed. I was there for a big part of many of the things that were going on. The tail end of sort of screen film technologies and the beginning of digital technologies in X-ray, but I spent a lot of time with MR and ultrasonic systems. Image science is cool because it blends medicine and biology with instrumentation, statistics, physics, and communications theory. There's a whole bunch of really broad spectrum things that kind of have to come together for this. And one of the things that we found in this particular study that we did is the physics of acoustic scattering present a very different relationship between the instrument and tissue properties compared with other modalities. So the way we did this for X-ray isn't going to work for ultrasound, and it's because information is encoded in variance, not in mean. So we get these quadratic test statistics, which have big impacts on how performance is rated. Beam mode imaging is only 1 to 10% efficient, sometimes less than that. So that's the largest loss is from this demodulation step that happens in image formation. So we think there's a really important role for signal processing after you do, first of all, how do you combine the elementary beams? How do you weight them, filter them individually, combine them in various patterns, and then maybe filter them afterwards? And all of that could have an enormous effect. And not only that, but beam forming strategies should vary with clinical exams. So as you walk up to an ultrasound scanner today, you generally push a button and say, I'm going to do breast imaging, or I'm going to do abdominal imaging, or kidney imaging. It only changes various things, but we can get really specific. If you want to say, I want to look for a lesion, or if I want to look at lesion boundaries or something, you can actually optimize that system in ways it doesn't cost anything. It's all software reformatting of the system. So we think that's really exciting. Performance is highly task dependent, so if I look at one thing versus another, I have to. The only way I can rate the quality of an imaging system is in the context of what I'm looking at. And that suggests that beam formation strategies are going to vary with clinical exam. As I said, we have tools to re-examine output guidelines. And I just want to finish by saying medical image science has developed to the point where it now guides, it does in X-ray, guides the development and evaluation of most imaging modalities. And we've tried to make our impact in ultrasound for that. So since I have a couple minutes left, I wanted to point out one funny thing that Bob was always told jokes. He was a very serious guy in a lot of ways, right, in science. Here he is standing on the beach in California with a drink in his hand, and we're discussing important things, right? So he was always having fun. So here's his paper. Was Unified SNR Analysis and Medical Imaging System. Very noble. What he proposed, what he actually sent to the editor at first was grand unified. Well, he's a physicist, so everything's a grand unified theory, right? And that. And he goes, no. Here's why I did it. If you take these acronyms and you get guano medical imaging systems, right? So if you don't know what that is, it's bat excrement, right? So he was trying to make fun of himself, a little self-deprecating humor, and he didn't want to tell anybody. He just wanted to put this out there, and then he could tell that story many years later. But the editor would have none of it. So he trimmed his title back, and that's where he was. Okay, well, thank you very much for your attention. Hi, Earl.
Hi. So, great talk. We enjoyed it.
Thank you.
I'm kind of observant myself. That second law is much more.
Yeah.
And it seems like it seems to be really a limiting factor in protecting those boundaries and edges and those steps. What's the effort these days to go on this thing? It seems like what you need is a bigger aperture. That is a limiting factor. And why not let it be that?
Yeah, well, the thing that I didn't bring up is the aberration the body provides, right? So just like in telescope imaging, you want to see point stars, right? But you got to go through the atmosphere. Same way, the body tends to give a sound speed like a random screen, right? So as you're passing this phase front through this random phase screen, it sort of messes up your focusing ability. So you can only focus so big, and so you're going to be limited in your total aperture because the apodization effects or the aberration effects worse as your aperture grows. There are, and I think the main problem right now is until we get 2D arrays that are functioning at real-time rates, which we can't do. There's many efforts to do this, but it's not fully functioning without doing a sparse array kind of analysis. It's the second, so when you only do one-dimensional, it's not quite enough, right? You need the second dimension. Plus, they're only doing phase correction, and I think they have to do some, Bob Wag at Rochester talked about doing some amplitude correction on each channel as well. So I think the solution will happen, I think, quite naturally with 2D arrays with both amplitude and phase correction adapted. And if we can do that in real time, we're done. Right now, the problem is if you want to have, say, 100 by 200, maybe a 1 or 200 by 1 or 200 element array. So that's 10,000 transmit-receive channels, right? And wire for each one of those. You got to put it in a little tiny wire that you can put on a patient. And then they haven't been able to figure out how to add that, high power sort of stuff without dissipating a lot of heat. So you start burning your hand when you hold these devices. I've been to Siemens and looked at some of these things, and they said, here, grab onto this. And you start going, and you go, whoa, it's getting hot. Yeah. So part of it is going to be just technology, interconnect technology, and sort of low power electronics has been solved. And sparse arrays. Yeah, people really look at sparse arrays, and there's been no solutions that people have found that have been satisfactory. I don't really have an analysis of what's limiting there, but they just, without side lobe cancellation that you get with sparse arrays, there's a problem. Yeah. Thanks. Any other questions? All right. Oh, yeah, go ahead. Sure.
So, you said you work with physicians to actually get those typical tests, those 5 tests identified.
Yeah.
Carry out the distinguished and this was based on discussion or how did that happen?
Well, it turns out about 1995, there's a guy named Stavros that wrote in Radiology, widely used clinical journal, what are the criteria for lesion detection? And he basically listed a whole bunch of them. So there was a lot of discussion amongst physicians. So I was working with Karen Linfers at UC Davis when I was there at the time, and we asked her, what do you think of these things, And she said, oh, this one's important and that one's not, and I said, well, tell me why. And so she started showing us images and cases and things. So it just came like that, basically, as she kind of put a rank order of what she uses in her practice for how she makes the diagnostic. It wasn't a detection problem some of them, like shadowing effects, and there were another vast array of things that we couldn't sort of codify into likelihood functions. But that was kind of fun to try to work with physicians and then see if we could write this into these conditional probability distributions. It was fun. Any other questions? All right. Well, thank you. Thank you for coming.
Is one good example of that. So even though it says it's about soybean seeds, you can think about biomedical applications and cancer pathology and stuff like that as well. So Matthew is currently a Department of Defense Fellow here at the University of Illinois and working in Professor Rohit Bhargava's group. He has a BS in chemistry and a BA in biology from St. John Fisher College in Rochester, and he got his PhD in chemistry from Michigan, where he worked in Raman spectroscopy. So we'll like you since you came here from Michigan. Don't go back. Matthew's won several great awards, including the University of Michigan Distinguished Dissertation Award, the Thomas Hirschfeld Award in Applied Spectroscopy, and the Casimir Fejan Award in Chemistry. So welcome, Matthew, and look forward to your talk today.
Thank you. Non-conventional Raman spectroscopy applications towards the compositional analysis of soybean seeds. So soybeans are actually a pretty big commodity here in the United States and worldwide. In the U.S., 76 million acres of land are devoted to growing soybeans, and this translates into about a $40 billion industry, 23 billion of which are exports. Now, in any industry, the goal is really to gain the most value from your product that you can. And in soybean seeds, not all soybeans are created equal. Premiums are paid for nutritional content. So a lot of work has gone into trying to develop approaches to quantify various nutritional components of soybean seed. So the things that people are interested in, buyers are interested in protein and oil content, as well as various amino acids, various fatty acids, and various sugars. And the current approach to analyzing soybean in a non-destructive way is near-infrared spectroscopy. So near-infrared spectroscopy is a type of spectroscopy that's been around since the 70s. It's underwent quite a bit of development. And right now it's the current industry standard. Now, I'm a big believer in Raman spectroscopy, and I think Raman spectroscopy holds a lot of potential for quantifying these specific components. Currently, protein and oil is the only thing that NIR can quantify to the industry needs, whereas Raman spectroscopy holds a lot of potential for amino acids, fatty acids, and specific nutrients like that. So in this talk today, I'm first going to go over an introduction to spectroscopy. Then I'll talk about how spectroscopy can give you chemical contrast. I'll follow that up with an instrument we built that demonstrates you can use Raman spectroscopy to quantify protein and oil content in single soybean seeds. And then I'll follow that up with an instrument we built for bulk soybean analysis. So what is spectroscopy? Spectroscopy is basically taking light, breaking it into its component colors, and trying to get information from those colors. So an example of how you get information from color, here's a picture of Waldo. Now, here, Waldo, is red, has a red shirt on with a red hat. But in this picture, you can't actually discern which one is Waldo. By adding color to this, you get information. Color gives you information. So here you can see Waldo's right there. So spectroscopy is converting light into color, light into information. This can be qualitative by observing what colors are present, or it can be quantitative by not only observing what colors are present, but also the intensity of those colors. Now, the human eye can actually only see 3 colors. It can see red, green, and blue. All the colors on the screen here are combinations of red pixels, green pixels, and blue pixels. Now, with scientific instrumentation, you can actually see a whole range of colors. a continuum of the electromagnetic spectrum where the visible region is actually a very small portion. So for the work that, for the spectroscopy that we do on soybeans, the near-infrared spectrum is right in this range. You can actually gain additional information by looking maybe out into the mid-infrared or using other parts of the electromagnetic spectrum. So the typical spectroscopy experiment would look like this. You would take a range of colors with known intensities. You would introduce it to a sample, and you would collect the light that comes out of the sample, and you would then ratio the light that went in to the light that went out, and that would give you an idea of how the sample modifies the light or how the light interacts with the sample. So a general definition of spectroscopy is the study of the interaction between radiation and an analyte as a function of wavelength. Now, if we were to do a spectroscopy experiment here on water, you would take a whole range of wavelengths, so the ultraviolet all the way out to the far infrared. You could put that through water, and then you could ratio the light that went in to the light that went out, and you would get a spectrum that looks like this. Now, this is actually 4 different types of spectroscopy. This is UV-vis spectroscopy, visible spectroscopy, near-IR spectroscopy, and IR spectroscopy. The method's the same. You ratio the light that went in to the light that went out, and ultimately the only thing that changed is the range of wavelengths that you put through your sample. So the range of wavelengths that you choose actually give you different chemical information. For example, UV visible spectroscopy is electronic spectroscopy, and what this does is light absorption is a result of electronic transition, so electrons moving from a ground state to a higher energy state. Infrared and Raman spectroscopy are vibrational spectroscopies. So what these are looking at groups of molecules and specific vibrations that are moving as a result of light incident on them. Now, Raman spectroscopy is different than the other types of spectroscopy I'm showing you here. With Raman spectroscopy, you use a single wavelength of light, and you put that single wavelength of light through your sample. So it's common to use something like a laser to get many photons at one wavelength, and then put that through your sample. So for an illustrative example, I'm going to use 785 nanometers as our Raman excitation frequency. So if you think in terms of photons, when a photon interacts with a sample, a couple things can happen. Number one, it could be absorbed. So if it's IR light, the light would be absorbed, and that would promote some vibrational states. If it's UV-vis or UV or visible light, that can promote electronic transition states, and the light's absorbed. If the light's not absorbed, one of 3 things can happen. The light will be scattered through the sample, and how it scatters depends on the molecules that are present. So the first type of scattering is Rayleigh scattering. With Rayleigh scattering, what happens is a photon comes in, it interacts with the sample, it promotes molecules to some kind of virtual energy state, and then the same photon comes off. So a 785 nanometer photon comes in, and then the 785 nanometer photon leaves the sample. Second type of scattering is Stokes-Raman scattering. And with Stokes-Raman scattering, what happens is a 785 nanometer photon might come in, and then it leaves some of its energy with the sample, and that results in a lower energy photon coming out. So this might be a 800 nanometer photon. Alternatively, you could have anti-Stokes scattering, and this is where a 785 nanometer photon will come in. The molecules are already vibrating because they're at room temperature, so the photon can actually gain energy from the molecule, and as a result, you would have a higher energy photon coming out. So if you put a 785 nanometer photon in, something like a 700 nanometer photon could come out. So what this looks like in terms of instrumentation is you would have a photon come in, 785 nanometers, interacts with the molecules, and then in the Raman spectrometer, if 785 comes out, this is Rayleigh scattered light, that gets rejected by the Raman spectrometer. Alternatively, a 785 nanometer photon could come in, interacts with the molecules. This time you have anti-Stokes Raman scattering, so it gains energy from the sample, and you have a 782 nanometer photon come out. This makes it through the Raman spectrometer and then gets sorted by wavelength. Alternatively, you have a 785 nanometer photon coming in, interacts with the molecules. This time it loses some of its energy to the molecules. As a result, you have a lower energy photon. That makes it through the Raman spectrometer, and it gets sorted by wavelength. Now, in reality, you have a laser, so you have billions and billions of photons interacting with your sample. The vast majority of those photons are actually Rayleigh scattered, so you don't actually look at those. Those get rejected by the Raman spectrometer. The ones that are Raman scattered make it through and then get sorted by wavelength. So a Raman spectrum looks like this. It's basically a histogram of photon counts that's collected over time. edge, you end up with a Raman spectrum that looks like this. So on this axis, you have Raman intensity, which is photon counts, and on this axis, you have a shift from an excitation frequency. So if we excite at 785 nanometers, you have an 810 nanometers to 915 nanometers, and this is generally considered the Raman fingerprint region. And it's usually reported in terms of wave number shift in order to compare different laser wavelengths if you excite with a different laser other than 785. So that is an introduction to spectroscopy and how Raman spectroscopy is different than the other types of absorption spectroscopy that are out there. Now, spectroscopy gives you contrast. So to compare the different types of contrast, I got a couple slides that just compare near IR to IR to Raman. So with near IR spectroscopy, the light tends to scatter more than it's absorbed, so you have a greater penetration depth. And this is the reason that near IR is commonly used in quality control applications for the agricultural industry and soybeans as well. Because the light scatters more than it's absorbed, it can go through very thick path lengths, and as a result, you can get the light through an entire soybean or through an entire apple, something along those lines. This spectral information arises from broad spectral overtones as a result, is it difficult to assign spectral features to specific chemical components. So the chemical information you're achieving here is basically groups of molecules moving together, and as a result, you don't know anything about the specific vibrations that are present. So they're spectral overtones. Light scattering tends to be a problem, so corrections are needed. So spectroscopy tends to follow Beer's law in order to do quantitative things. And in Beer's law, you need to know the sample path length. So because the light scatters, it doesn't go directly through the sample, so you don't really know the path length. There's a lot of very good corrections for scattering regimes that actually work pretty well in the near IR, but this is something to consider if you're doing near IR spectroscopy. IR spectroscopy, light tends to absorb more than it's scattered, and as a result, you have very little penetration depth. And for this reason, in order to do IR spectroscopy, you have to work on very, very thin samples. Samples tend to be on the order of maybe 5 to 10 microns thick. The spectral information arises from specific vibrations arising from molecular functional groups. As a result, you can assign spectral features to specific chemical components. So the chemical specificity in IR spectroscopy is superior to that of near IR spectroscopy. Sample thickness and preparation tends to be the biggest difficulty with IR spectroscopy. So if you want to take IR spectrum of something like tissue, you have to microtome it to fairly thin sections, and you also have to make sure there's not a lot of water present, because water has a very large absorption in the infrared regions. Now, Raman spectroscopy is actually the best of both worlds. With Raman, you can use any wavelength you want. So you can choose a 785 nanometer laser, a near IR laser, that achieves the penetration depth that you gain with near IR spectroscopy, but at the same time, it's also a vibrational type of spectroscopy that gives you similar chemical information to what you achieve with mid-IR spectroscopy. So you have very high chemical specificity in the Raman spectrum. Now, the quantum efficiency of Raman is low, and that's why it hasn't really been developed for things like agricultural applications where you're analyzing whole soybeans. Quantum efficiency being low means it's a low light event. You need very, very sensitive detectors. You need very high-powered lasers in order to get nice Raman spectra. And the reason that it's actually applicable in the research I'm showing you here is because detectors, lasers, filters are becoming better and better each year, and as a result, we're able to do things that we couldn't have done 20 years ago. So, all spectroscopy follows Beer's law. So I'm going to show you some calibration curves in future slides here. And these calibration curves are based on this principle, where you have a concentration. So you can get the concentration using wet chemistry approaches. And you have basically a known amount of a sample that you're looking at. And then what you do is you take a spectrum of that, and that spectrum gives you a response. And this response is going to be linear. So then what you can do is use this linear relationship. So you get an equation for this line, and you can take a spectrum, follow that over to the line, and then figure out what the concentration is. So that's how you quantify using both near IR, mid-IR, and Raman spectroscopy. Now, conventional Raman spectroscopy, as well as mid-IR, and not so much near IR, you can do spectral imaging. So spectral imaging is basically getting your spatial resolution using point mapping, and then getting a spectral resolution by taking a spectrum at each one of these points. So you get your X, your Y, and then your Z-axis is going to be a spectrum. Okay. So in conventional Raman spectroscopy, what happens is the light would come in, it goes through a lens, it focuses to a point, the Raman spectra is generated, the Raman signal scatters in all directions, that gets collected by the lens and then goes back up to a Raman spectrograph. Now by taking multiple points over time, you get a spectrum at each one of these points here, and you can put together a map of Raman spectra that looks like a Raman image that you see here. And in order to visualize the distribution of chemistry in this image, you can pick a couple spectral bands, and I chose red, green, and blue because those are the colors your eyes are sensitive to. And this gives you an idea of the distribution of chemistry within the soybean sample. So if you compare the three different types of spectroscopy, you have near IR here. You can kind of see the distribution of chemistry shown by the near IR spectrum. Here you have a mid IR spectrum, and you can see there's a lot more information here. There's a different distribution than what you're seeing in the near IR. And then here's a Raman image of the same soybean section, and you can see there's pockets of, I guess, teal here and orange here. Those correspond to sugars. The purple here and the purple here correspond to oils, and the red might correspond to protein and various different chemistries. So understanding the relationship between what spectral bands you observe in the Raman spectrum and the image, you have to kind of look at known standards in order to figure out what you're actually visualizing in this distribution. So using the mid-IR spectra or imaging, we can visualize the distribution of protein and oil in soybean sections, and we see that the distribution is actually fairly heterogeneous. It's not a uniform distribution of protein, and these are 4 different soybean sections that we took infrared images on. You can see this soybean section, which has a protein content of about 50%, has these splotches of protein here, whereas this one that has a protein content of 51% has actually large pockets of protein, whereas the other portions of the seed are low in concentration. So what this means is if you use conventional Raman spectroscopy to develop a calibration model, if you took just a point spectra here, you would get a very different calibration than if you took a point spectra here. So you need to take representative sampling of the soybean in order to actually develop a proper calibration model. So in order to do that, we turn to actually transmission Raman spectroscopy. So conventional Raman spectroscopy, if you take a point sample on an entire soybean, what you would get is a signal that's actually surface weighted. So we have a pharmaceutical capsule here that has a gel cap, and then inside is a powder that has pharmaceutical ingredients. And if you take conventional Raman spectra, what you end up seeing is basically just the gel cap. This is a fluorescence signal that arises from this gel cap. If you take a spatially offset Raman measurement, so this is different than a conventional Raman approach, what you would do is you would illuminate in one position and then collect spatially offset from that. And the idea is that because this sample is light scattering, the photons would diffuse through the sample, and then if you collect offset from that, you would get some kind of representative sampling from the path that the photons took in the diffusion process. And through this approach, you end up getting a spectra that looks like this. So you actually do get some of the active pharmaceutical ingredient in this Raman spectrum. Now, if you take a transmission approach, so you basically take the illumination and bring it down to the bottom, you end up getting a much better representative sampling of this pharmaceutical. So that spectra looks like this. So taking a similar approach with soybeans, the idea was we could take a representative sampling of the soybean and then get a representative spectrum that we could develop calibration models on. So this is actually a general problem. Like we apply it to soybeans, but it could be applied to process analytical technology, where you might be looking at fluids mixing through tubing. You could use it for biomedical applications, where we've actually used it to recover bone spectra through the skin. You could use it in pharmaceuticals, where you want to look at the distribution of active pharmaceutical ingredient. Or we're using it in soybeans here, where we're trying to quantify economically and nutritionally valuable components of soybeans. So light scattering it looks like this. If you have no light scattering, what I have here is a beaker full of water, and I have just the Illinois emblem inside the beaker. And if you increase the scattering, it's pretty clear that you can no longer actually see this eye emblem. And the reason for that is because the light, as it travels through the beaker, ends up spreading out, diffusing, and you can't actually image anything inside of that without doing some kind of math on it. And then this is what it looks like in a cuvette. You have a cuvette full of water, and then if you increase the scattering, you can see the laser beam profile spreads out, diffuses as the scattering levels increase. Now, the reason this is important for Raman is you're only going to get a Raman signal where the where the excitation photons actually propagate to. So in highly scattering systems, you can see the laser actually spreads out and propagates pretty significantly, which means if this was a soybean, which is highly light scattering, you would get laser light kind of spread out throughout the entire soybean. And then there is some Monte Carlo modeling that basically demonstrates that you get representative sampling in a transmission approach. So here we have a light scattering sample, and what we're showing is a histogram of where the Raman photons actually come from. Okay, so the single soybean instrument. Okay, so on that last slide, I showed a Monte Carlo simulation. We actually did this for soybeans. So here we took a CT scan of the soybean in order to figure out what the internal structure of the soybean looks like. We then generated a computer mesh so we can model photons propagating through the soybean. We labeled this with the proper absorption and scattering coefficients. We then illuminated a soybean on one side, and we just watched the photons randomly walk through the soybean, and had a detector that had a certain numerical aperture, and we figured out where the Raman photons originated that we actually detected. And if you look at a histogram of this, so this cross-section through the sample here, you end up seeing something like this. So you end up getting photons largely concentrated in here, but you also get some from the surrounding area too. And this is center weighted as opposed to being surface weighted. So if you look at a soybean actually has this outer skin on the outside that isn't useful. So you would want to get all the information from the interior of the soybean and not the exterior of the soybean, which is what conventional Raman spectroscopy would give you. Then I got an image here of a soybean that we illuminated with 785 nanometer light. This is 200 milliwatts, and you can just see it's kind of glowing red, and this just kind of supports the idea that the photons just diffuse and bounce around throughout the entire soybean. Okay, so we wanted to see, can we actually collect a Raman signal from the soybean? So in our first set of experiments, we had a 785 nanometer laser that was focused onto the back surface of a soybean, and then we just collected all the light that came out of it. And we ended up seeing spectra that looked like this. Now, each one of these spectra took an hour to collect, and that's largely because of the inefficiency of our setup, and this was only a 40 milliwatt laser. But we get a definite Raman spectrum from 4 different types of soybeans. So you get a phenylalanine band here, which corresponds to protein as well as the amino acid phenylalanine. You get CH2 bands, and you get Raman spectra. This is a Raman spectra that is recognizable. But the acquisition time was quite long. So based on that data and some of the simulations that we did, we were able to apply for funding, and we got funded to put together an instrument that could measure Raman spectra from single soybeans efficiently. So this is the instrument we ended up building, and what you have here is you have a sampling stage, and the sampling stage consists of a series of holes that you would put the soybeans into, and then there's a hole that passes through this plate. The laser light comes from the bottom, illuminates the bottom of the soybean. This is a collection lens that is automated. It moves up and down and focuses onto the soybean. Then that light gets collimated from the sample, goes to fiber optics here, which brings it down to the Raman spectrometer. So this thing's automated. It's controlled by LabVIEW. We're able to load it up with soybeans, set whatever parameters, and then come back maybe the next morning, and all our data is stored in the computer. So with this, the spectra that we acquire with this instrument looks like this. This is a hyperspectral system, which means that we collect about 250